Welcome to Programming Fluency. This is section 6.4, Pointers and Const. You have seen that when a function receives an array as a pointer, it can modify the original elements. That is powerful, but it is also risky. In this video, you will learn how the keyword const lets you lock down a pointer so accidental writes become compile errors. Let's begin. A function that receives an array as a pointer can change the original data. That is powerful, but it is risky. Now you will learn how the keyword const lets you lock down a pointer so accidental writes become compile errors. Let's begin. This is the plan for this video. We start with why const matters for pointers. A pointer gives you two separate things you can lock down: the data it points to or the pointer itself. Next, a pointer to const, written const int star p. This makes the data read only. You can still move the pointer, but you cannot write through it. Then a const pointer, written int star const p. This is the opposite. The pointer is fixed in place, but the data it points to can still be changed. After that, we learn to read declarations from right to left. This simple trick lets you tell the three forms apart at a glance. Finally, we look at const correctness in practice. You will write read-only parameters, and we point out the two mistakes to avoid. Why do we need const with pointers? When a function receives an array as a pointer, it can modify the original elements. That is powerful, but it is risky. Imagine you write a function that only reads an array. It computes a sum, or searches for a value, or prints the elements. Nothing stops a typo or a copy-paste error from accidentally writing to the array. The compiler will not warn you, and the bug may go unnoticed until the data is silently corrupted. The keyword const solves this. It lets the compiler enforce your intent, so a pointer that should only read can never write. You already know const as a way to make a variable read only. With pointers, const becomes more nuanced. There are two separate things you can lock down. First, the data the pointer points to. Second, the pointer itself, meaning the address it holds. So const int star p and int star const p look almost identical, but they mean very different things. One prevents you from changing the data. The other prevents you from changing the address. Getting them right is a professional skill called const correctness. Let's start with the first form. A pointer to const is a pointer through which you cannot modify the pointed to data. The pointer itself can be redirected to a different address, but you cannot use star p equals something to change the value. Pointer to const, written const int star p, is a pointer through which the pointed to data cannot be modified. Star p equals value is a compile time error, but the pointer itself can be reassigned to point at a different address. Let's trace a program. We declare x as 10 and y as 20. Then const int star p equals the address of x. We can read star p, which prints 10. If we uncomment star p equals 99, the compiler rejects it with a read-only location error. But we can redirect p to point at y, because the pointer itself is an ordinary variable. Now star p reads y and prints 20. The output has two lines. Star p is 10, then star p is 20. The data is protected, but the pointer can still move. Now an important subtlety. Writing const int star p equals the address of x does not make x itself const. You can still write x equals 99 directly. The const only restricts what you can do through the pointer p. It is a promise about one particular access path, not about the data itself. So star p equals 99 is an error, but x equals 99 is fine. After that, printing star p shows 99. Because p still points at x, this may seem contradictory, but it is by design. The pointer promises not to modify x. Other code can still modify x through its own name. Now the second form. A const pointer is a pointer that cannot be redirected. It always points to the same address, but you can modify the data at that address through the pointer. A const pointer, written in *const p, is a pointer that cannot be reassigned after initialization. P equals a new address is a compile time error, but the data it points to can still be modified through *p. The pointer is locked to one address for its whole lifetime. Let's trace the const pointer. We declare x as 10 and y as 20. Then int *const p equals the address of x we read *p, which prints 10. Now *p equals 99 works fine because the data is not protected. So x becomes 99. If we uncomment p equals the address of y, the compiler rejects it because the pointer cannot be moved. The output has two lines. *p is 10, then x is 99. This is the opposite of the pointer to const. Here the pointer is locked, but the data is free. The difference between const int *p and int *const p is easy to confuse. A reliable trick is to read the declaration right to left, starting from the variable name. For const int *p, read p is a pointer to a const int, so you cannot modify *p, but you can redirect p. For int const p, read p is a const pointer const to int, so you can modify *p, but you cannot redirect p. The third form, const int const p, locks both. You cannot modify the data and you cannot redirect the pointer. It is the most restrictive form. There are three ways to use const with a pointer. The first one is const int *p read it right to left. P is a pointer to a const int, so the data is locked. You cannot change the data through p, but the pointer is free. You can point p to another place. The second one is int const p read it right to left. P is a const pointer to int. Now the pointer is locked. P always points to the same place, but the data is free. You can change the data through p. The third one is const int const p. Both const keywords are there, so both are locked. You cannot change the data and you cannot move the pointer. This is the most protected form. The most important use of const with pointers is in function parameters. When a function takes a pointer but promises not to modify the data, you declare the parameter as a pointer to const. Compare these two signatures. Void modify array takes int r. That declares intent. This function might change your data. Void print array takes const int r. That declares a promise. This function only reads your data. And the compiler enforces the promise. If print array tries to write r at index I equals something, you get a compile error. Let's see const in action. Inside print array, r is a pointer to const. Reading r at index I is fine, so the loop prints every element. But writing r at index 0 equals 99 would be rejected by the compiler, because r points to const data. The main function makes an array and calls print array. The output is the 5 numbers 10, 20, 30, 40, 50. The const catches accidental modifications at compile time before they can cause runtime bugs. This is the value of const correctness. Const correctness has one more benefit. You can always pass a non-const array to a function that expects a pointer to const. That works because adding const is a narrowing of permissions. The function promises to do less than the caller allows, so it is safe. Going the other direction is not allowed. You could not pass a const array to a function that takes a plain int star because the function might modify data that was declared read only. The compiler warns or errors on that conversion. The rule is simple. You can always add const to make a promise, but you should not remove it because that breaks a promise. The C standard library applies const correctness consistently. Look at these signatures from string.h. strlen takes a const char star because it only reads the string. strcmp takes two const char star arguments because it reads both and modifies neither. strcpy writes to dest, which is non-const, and reads from src, which is const. mempb follows the same pattern. So the rule is const on source parameters, non-const on destination parameters. This is the universal convention, and see every function you write that takes a pointer should follow it. Ask yourself, does this function modify the data? If no, add const. If yes, leave it off. Let's summarize what each form allows in one table. Pointer p of type const int star can read star p and can redirect p, but cannot write star p. Pointer q of type int star const can read and write star q, but cannot redirect q. Pointer r of type const int star const can only read. It cannot write and cannot redirect. Const before the star restricts data access. Const after the star restricts pointer reassignment. Both const keywords restrict both. This is the most common mistake, confusing the two forms. You write const int star p, then try p equals the address of y and star p equals 99. You expected the redirect to fail and the write to work, but it is the opposite. Const int star p means pointer to const int. The data is const, the pointer is not. So redirecting p compiles fine and writing star p is a compile error. If you wanted a fixed pointer, you need int star const p. Always use the right to left reading rule to check which const applies to what. Now a second mistake, casting away const. You write a function that takes a const int star, then cast it to a plain int star and write through it. The code compiles and appears to work, but if the original data was declared const, modifying it through the cast is undefined behavior. The compiler may have placed the data in read-only memory. The program might crash, silently corrupt data, or work on your machine but fail on another. Const in a parameter is a promise, and casting it away breaks that promise. The fix is simple. Do not cast away const. If you need to modify the data, the parameter should not be const in the first place. Fix the signature instead. Let's recap. Const with pointers creates two distinct restrictions. Protect the data or fix the address. Const int star p, a pointer to const, prevents writing through the pointer but lets you redirect it. Int star const p, a const pointer, prevents redirecting the pointer but lets you write through it. Const int star const p locks both. Read declarations right to left from the variable name to tell which const applies to what. And const correctness means marking every pointer parameter as const when the function does not modify the data. Never cast const away. Next, you have learned what pointers are and how const controls access. But where do all these variables actually live? In the next section, you will explore the memory layout of a C program, the stack and the heap.